where we're going to attempt to verify the law of conservation of momentum. Listen, we know that the law of conservation of momentum is true, right? Pi equals Pf. If we have an isolated system, we're just going to show that it's true today, show that it's correct today, so you're not just taking my word for it. At least that's the goal. Now, we always have a problem when we do a lab, and it's always phrased in the form of a question. I'm giving you the problem this time, phrased in the form of a question. Just remember, another time we do a lab, I might not give you the problem. I might just tell you, this is what it's about, you identify the problem. And remember, when you do, to phrase it in the form of a question. Now, the next thing that we are going to do today is identify the variables. The one manipulated variable that we have, remember, the manipulated variable is usually the variable that you change, but it doesn't have to be. It's the one that causes another change, which is usually as a result of me doing it, but not always. Okay? The one that causes another change. In other words, the one that causes the one responding variable to change. The responding variable changes in response to the one manipulated variable. Don't identify more than one of each of those. Those should become pretty clear to you, by the way, as we go through this little pre-lab lecture today. Hopefully by the end of it, before you even go into the lab, you know what the manipulated variable is and what the responding variable is. There's 1,000 control variables. I don't expect you to list 1,000 of them. If 500 is good, or even 2 is good, or even 1 is good. It depends on what the really important ones are. Should we keep the humidity the same throughout this entire experiment? Yes. Should we keep the temperature the same throughout this entire experiment? Yes. Do I need to see those listed as control variables? No, I don't. Those are really not going to make any real difference, right? I need you to list the 1 or 2 control variables that will make a big difference, that will really affect this. Does that make sense? List the 1 or 2 that are going to make a big difference. I'm not going to tell you exactly how many there are, because I might give it away if that's the case, but there's not going to be very many that you need to list. There's tons of them that technically we're controlling, but only 1 or 2 that we really, really have to focus on. And again, that should become fairly clear to you, I hope, as we go through the pre-lab lecture here. So, problem variables. Now, the next thing that I've listed here is procedure, but the procedure actually has a picture of the apparatus. The apparatus that you're going to use is a track. You don't have to list the materials or the apparatus. Okay, I'm just telling you what's there. There's a track, an aluminum track, and then each group is going to use 2 of these smart cards. You guys all used these last year in Physics 20, regardless of whose class you were in, whether it was first semester or second semester. Today you're going to, for the first time, use 2 of them in the same experiment. So track, 2 carts. You notice on one of those carts is a little mass. It doesn't matter whether it's on the red one or the blue one. You choose. But just make sure you keep that constant the whole time throughout the entire experiment. You wouldn't want to change that. And in addition to that, you've got your phone here. I asked you last night, I sent a message last night to you to download the SparkView app. If you weren't able to do that, that's okay. It's not the end of the world. Okay, in all likelihood, there'll be somebody in your group that has it, and that's really all we need is one person in the group to have the app. I just asked everybody to do it last night if they could, so that we could be more assured that one person, at least in each group, would have it. So you've got your phone that you're going to connect via Bluetooth to both of these carts, and these carts, which are going to be on this metal track, which is presumably going to be on a level surface. That's the goal, at least. Okay, if it's not level, then try to make it level by sticking something underneath it, a few pieces of paper or something like that underneath it. Now, one thing that I want to say before we move on and actually talk about the procedure is these carts are almost $300 each, and they're made out of plastic. They break easily. If you drop it off of the lab bench, we're going to do this in the biology lab, if you happen to drop it off of the lab bench, it might break. You don't want to do that. Okay? I don't want you to do that. So what I want you to do when you're not using it is to put these carts upside down on the bench. Why upside down? So it's not going to roll with the wheels, right? Okay, if the bench isn't quite level, or if somebody bumps the bench, you could easily just roll off the side and break it, right? Put it upside down so that the wheels are facing up. Or if you're about to use it, make sure, and it's on the track, make sure that somebody is standing at either end of the track in case it happens to roll off. You don't want it to roll off the track. Does that make sense? It's not a big deal. Okay, nobody in Alaska had any issue with that. Everybody did things just fine, and nobody broke anything. And I don't anticipate you guys would do that either. Now, what's this procedure going to look like? It's actually pretty straightforward. One of these carts is going to remain at rest. It doesn't really matter which one is which. Okay, the blue one or the red one. One of them starts at rest. One of them, you're going to give a little push. In other words, you're going to give an initial velocity to one of them. So let's say in this case, the blue one is cart number 2. That's the one that's starting at rest. The red one is cart number 1. That's the one that's going to start with an initial velocity. By the way, I don't care which cart is which, but you have to recognize which one is which and identify which one is which, right? And the one that starts at rest, you're going to call cart number 2. Whether it's the blue or the red one, that doesn't matter. But the one that starts at rest is going to be called cart number 2. The one that starts with an initial velocity, whichever one that is going to be called cart number 1. Now, I'm going to give cart number 1 a push toward cart number 2. So it's got a velocity. And then it's going to collide with cart number 2, and it's going to stick to it. The reason it's going to stick to it is because there's Velcro here and here. Now, make sure that it's the right side of the Velcro, right? Like, make sure that you don't have the two pieces of Velcro that are the same that are hitting each other, because they're not going to stick together. We want them to stick together, right? So push cart number 1, it's going to move down, it's going to collide with cart number 2, and then they're going to head off as one object. You're going to collect the initial velocity data for cart number 1, and you're going to collect the final velocity for both carts as they move off together. Now, how are you going to do that? Well, you'll see in a minute. Does it make sense conceptually what you're going to do, though? Give one a push, collect the initial velocity, they collide, they head off as one, collect the final velocity of both carts combined. And then, by the way, you're going to repeat it, but you're going to repeat it giving cart number 1 a little bit of a different push, and therefore a little bit of a different initial velocity. So each time, with each trial, you're going to have a slightly different initial velocity of cart 1, and then as a result of that, you're going to have a slightly different final velocity of both carts combined. Do it 7 to 10 times, 7 to 10 good trials. Okay? If you have time, go 10. If you're a little bit crunched for time, 7 would be okay. The minimum we want to use is about 7 trials. We're going to plot a graph here, right? And the more data points we have on the graph, the better this is going to work out to be. So how do we collect data? This might look familiar to you. Hopefully it does a little bit. You guys used this last year. When you get these carts, you're going to turn on these carts. One red one, one blue one. You're going to turn them on. And you're going to click on the app on your phone. And when you do that, you're going to get a page that looks like this. You're going to click on Sensor Data, right in the middle there. Now, when you click on Sensor Data, there's 3 columns that appear. These 3 columns. The first column is which device or which carts you're connecting to. In Physics 20, you always connect it to one cart. Now you're going to connect to 2 separate carts. Just make sure you connect to the 2 correct carts. There's 8 carts in the lab. They're all relatively close together. You might see 5, 6, 7, 8 options to connect to. Make sure you connect to the 2 carts that you're using. And you can tell which 2 carts they are because there's numbers on them, and you can read that and compare them with that. Does that make sense? So make sure you connect to your carts. Now the second column involves what data you're collecting, what you're measuring here. In Physics 20, most times you collected position, not always, but most times you collected position. What I want you to do today is to turn off the collection of everything. Click on all these bullets here. Turn off everything except velocity of cart 1 and velocity of cart 2. Those are the only 2 things that you need to measure here. The velocity of cart 1, which I think for me was the red one, and the velocity of cart 2, which I think was the blue one. For you, it could be the opposite, whatever. As long as you keep that straight, doesn't matter which is which. Now, the third column is just simply what you're going to display real time as you're collecting data. What I want you to do is click on this option here, which is the table and the graph. It doesn't really matter what you're displaying because it's going to collect all the same data regardless of what you display. It's just easier to get the data, to view the data, to interpret the data if we select the table and the graph, right? That's how you set it up. When you finish clicking on that, you're going to go to a page that looks like this. Although this is the page you'll see with data already collected. Okay, when you go to that page initially, you're not going to see a graph there, and your table that's right beside it is going to be completely blank. When you're ready to roll here, you press the start button. You give cart number 1 a little push. It collides with cart number 2. They move off for a little bit. Then you press the stop button. And you should see 2 graphs that look something like this. Maybe not exactly like this, but something like this. These 2 graphs here show me the initial velocity and the final velocity. We're going to interpret these graphs here now together, and then we're going to see how to determine exactly what the numbers should be, exactly what numbers we should write down. You're not exporting data here into Google Drive like you did last year most times. You're just recording it on a piece of paper right off of the screen that you see on the board here right now. All right. Listen, we got some stuff going on right here, like right in here. Can anybody tell me what's happening right in here before that black line? Nothing. Right? Look, cart number 1 is at rest. Cart number 2 is at rest, 0 meters per second. And then we can see that there's movement. Right? The movement is when I gave cart number 1 a push. Tell me which one you think is cart number 1. Which one is the one that I gave a push to? The red one or the blue one here? The red one. You can see that the velocity of the red one is increasing. It's increasing in the negative direction. It just means the red cart is going backwards. That doesn't matter. Okay, I want you to take the absolute value of the velocity, make it the speed. It doesn't matter which direction it's going, okay? So this says negative whatever, just make it positive. You can see that the velocity is increasing, 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 and then it reaches a peak speed, and then it decreases and levels off. Well, that should happen to the car that you push, right? The car that you push is going faster, and then it collides, and what happens when it collides? It slows down and heads off together with the other one. Now, look at this value right here. This looks to be about 0.4, negative 0.4, because it's going backwards. What's this value? About 0.4? What does that tell you? Sorry? It tells you that you're probably correct here, yeah. But it also tells you, no, it doesn't. It's correct that the forces are equal, but this doesn't tell us that. This tells us that after the collision has taken place, in this section here, they headed off as 1, right? The same velocity. What is it, 0.4 meters per second? Make sense? So this is my initial velocity right here, and this would be my final velocity right here. The good news is you don't have to estimate what it is from the graph. What I want you to do is look at your actual data table. Look what's happening here. This is the red one here, and this is the blue one. You can see that the red one is increasing, right? Increasing, increasing, increasing. The blue one is 0, 0, 0, 0. Oh wait, the blue one's not 0 anymore. What just happened? It just got hit. So now the blue one starts moving. The initial velocity of the red cart is this velocity right here, 0.601 meters per second. Why did I say it's 0.601 meters per second? Because that's the speed it was moving just before it hit. Can you see that? Just before it hit, 0.601 meters per second. So I would record for this, for my data table, which you'll actually see on the next page, V1I, 0.601 meters per second. I drop the negative, right? They're both going in the same direction, drop the negative. Now, what's VF? 0.012? No, we're not there yet. The collision takes a little bit of time. We want to know what the velocity is, not during the collision, but immediately after the collision. Let me press the button here to go to the next page where I've just simply scrolled down the data table here. Look at this. Remember, this one is red, this one is blue. Look at what happens at 2.6 seconds. Those two velocities equal each other. 0.365 meters per second. You see that? That's how fast they're both moving after the collision. So to find VI, what you're looking for is the velocity of cart number 1 just before cart number 2 began to move. Got it? And to find VF, you're looking for the velocity at the time where they end up being the same, or at least close to the same. If one is 0.365 and one is 0.366, that's fine. Okay, they might not measure quite the same thing. But when they become either the same or virtually the same, then that's going to be VF. Does that make sense to you guys? Okay, so we know what V1I was. VF here would be 0.365 meters per second. And then I would move on to the next trial, changing the value of V1I just by giving it a little bit of a different push and seeing how VF of both carts responded to that. You're going to have 10 of these trials. And when you get 10 of these trials, fill in the table here, right, with all 10 trials, both masses. I've got mass 1 labeled as red, mass 2 labeled as blue, but if you reverse that, that's okay. As long as mass 1 is the one that you pushed, and as long as mass 2 is the one that was hit. Okay? Doesn't matter which one's blue, which one's red. Doesn't matter which one's heavier. Okay, mass 1 might be heavier, mass 2 might be heavier. Doesn't matter, as long as you've got that stuff kept straight yourself. Fill in this table, and then plot a graph. Your graph is going to be final velocity versus initial velocity. You've never seen a graph like that before. You've never seen final velocity versus initial velocity. The good news is it's a straight line. And a straight line is always expressed by the equation y is equal to mx plus b. In fact, Google Sheets will give you the equation for this graph. It'll tell you the value of m, the slope, and the value of b, the y-intercept. The value of b is going to be pretty close to 0. It should theoretically be 0, but probably won't be exactly. Close enough that we can consider it to be 0. The slope of the graph is going to be given to you, and you're going to use that number. But how? What does the slope represent? In Physics 20, you learned that the slope of a position-time graph was velocity. How did you know that? Because your teacher told you that. That's it. Because your teacher told you, and you believed us. We weren't lying, it's true. But you didn't know it because you figured it out. We're learning today how to figure out what the slope represents. Now, by the end of this, I'm going to go through 3 or 4 minutes here of explaining how to find the significance of the slope. I don't expect you to be able to do this on a test tomorrow. I hope by the end of this, what I've done made sense. We'll do it enough times this year for different graphs that you should be able to eventually do it yourself. I don't expect you to be able to do it yourself right now. Today, basically, I want you to follow along and just copy out what I write when you do your lab report. Okay, so here's what we do. We make 2 columns over here beside the graph. In the first column, we write down y is equal to mx plus b because it's a straight line. And then when we replace y, this is from math class, right? Grade 9 math. Y is equal to mx plus b. We replace y with VF because VF is what's on the y-axis. We replace m with the word slope. Technically, we don't have to replace that, but I like to do that because I don't want to get slope mixed up with mass, right? In math class, you call the slope m, but in physics, we use mass a lot, so you might get it mixed up, right? I'm just going to write the word slope in it. The x-axis of this graph is the initial velocity of cart 1, so I'll call it v1I. And we already said that the y-intercept is going to be 0, or at least pretty darn close to that. So I'll just cross that off. In the next column, you want to come up with an equation from class. Maybe it's on your data sheet, maybe it's not, but one that we've used in class that has both VI and VF in it in the context of a collision. So what equation has both VI and VF in it in the context of a collision between two things? Yep. Okay, that would work actually. Okay, that's not the one that I want to use here, because usually in the context of a collision, although we can use impulse, usually we're going to use conservation of momentum. Okay, so PI is equal to PF. That's M1 V1I, the one that I push, plus 0, the one that was at rest initially, equals, I want to call it mass total times VF. The red car plus the blue car, plus whatever mass was on top of it, times VF. And now I just want to rearrange this to solve for VF. Why? Well, because that's what I solved for right there. So VF is equal to M1 over MT times V1I. And now, here's the crux of it. Cross off VF. Why? Because it appears in both. Cross off V1I, because it appears in both. What am I left with? I'm left with the slope and M1 over MT. So the slope of this graph is equal to M1 over MT. You would have never predicted that, right? Slope of a position time graph is velocity. We know that. The slope of a velocity versus velocity graph is mass 1 over mass total. How would we have ever predicted that without having some way to figure it out? Has that made sense to you? If it did, good. That's as far as I need you to be with this technique today, is for it to have made sense. I'm not going to ask you to do this again tonight or tomorrow night. You can just copy this out for your lab. The time is going to come where you'll have to do it yourself. But we'll have more times of practicing it before I expect you to fully do it yourself. All right? So as long as it made sense to you, we're okay right now. That's exactly where I want you to be. If it didn't make sense to you, then either ask me now, or you can ask me later and I can work through it with you again. All right. We know the value of the slope, right? Google Sheets gave it to me. We know the value of M1 over mass total, or at least we can find it, by calculating it. Right? You know the masses, you just do the division. Those two numbers should be equal. The slope should be equal to M1 over MT. If they are, then we've just verified the law of conservation of momentum. Why? Well, because look at what we assumed over here. I assumed that momentum is conserved, PI is equal to PF. If those two numbers are equal, then my assumption is correct. If those two numbers are not equal, then my assumption was wrong. So if they're equal, momentum is conserved. If they're not equal, the momentum is not conserved. All right? Make sense? Now, realistically, it's not going to be exactly equal, right? It's not going to be perfect. Like, if it is for you, then that's amazing. It's almost certainly not going to be exactly equal. So here's what we're going to do. We're going to calculate the percent difference here. The actual minus the theoretical over the theoretical, takes the absolute value of that, times 100. You guys recognize that from chem class? You've seen that before? The slope is the actual value, and your calculation of mass 1 and mass total is the theoretical value. Like if you get 0%, then Well, those two numbers are exactly equal, right? Here's our cutoff, though. We're going to say if the percent difference is less than 10%, they're close enough to say my assumption was correct, and therefore momentum is conserved. If it's bigger than 10%, we'll say momentum is not conserved. The assumption that I made was incorrect. And that's okay, that's a valid conclusion. Even though we know that shouldn't happen, we're not going to base our conclusion on what we think is going to happen. We're going to base our conclusion on our data. Got it? You will get full marks if you say momentum was not conserved and I just disproved the law of conservation of momentum if your percent error was 14%. If you got 14% and said momentum was conserved, you won't get full marks because it's inconsistent. Finally, you write a conclusion. We don't have a hypothesis for this, so our conclusion is going to relate directly back to our problem. Was it conserved or verified? Yes. The law of conservation of momentum was verified. We know this because the percent difference was less than 10%. It was 8.3%. Or no, the law of conservation of momentum was disproven. We know this because the percent difference was 79.2%. Hopefully it's not that big. If it's that big, you probably made a mistake somewhere in your collection of data. And of course, sources of error. As much as sometimes you might think Scott to be a source of error, or Marcus to be a source of error, or any of you guys to be a source of error, you're not. None of you are a source of error. Don't list human error, okay? We're listing things with the apparatus. We're listing things with the procedure. We're listing things with the conditions in there. Our time management, okay? Something like that. Suggest improvements as well. So if you identify a source of error, good. Suggest an improvement for that. If you catch the source of error partway through the experiment, fix it. You can still mention it here. Right? You don't have to leave it and say, oh, next time I'll fix it this way. Just fix it and say, this is the way I fixed it. Now, all of you already have on Google Classroom a template, and your template is going to look like this. A lot of purple there, it's just instructions. Tells you need a problem, variables, and so on. Everything that you see in your template, you need. If you don't need it, I'll delete it. But I want you to delete the purple there. The purple is only there for information purposes, for you to be reminded of some things. In addition, you're going to see the rubric, which is pretty specific. So go through that rubric and when you're finished your lab, and make sure that you've got everything. Okay? Try to mark it yourself. See if you could get a 28 out of 28 or whatever the case may be.